Okay, so this is the section 2.2 notes from Calculus 1. The previous section, which was mostly about discovery of limits, I did briefly talk about the formula or definition of a limit, but now we're going to talk about it in great detail and how it's used in calculus. So this is your big definition right here. So the formula is right here. So I'm gonna read it as if the same way we talked about it in the last lesson. What does this mean? So you have a function, and they're saying the limit, which is the LIM, as x approaches some value, will be equal to L, which is what we call the limit of the function. Now, most students, when they see something like this, it is like mind-boggling in terms of crazy formulas, no numbers, just a bunch of crazy variables, right? So I'm going to try to break it down for you to make life a little bit easier, right? So if you're looking at this formula, basically this value of a right here is always going to be some value of x. So it'll be a number of some kind in which you're basically moving along the x-axis to find where the limit is going. So f of x is just going to be some algebra equation, basically, usually, or algebra expression, better way to put it. And L is always going to be some value of y. You're going to note that I'm going to refer to the term height a lot because it helps students understand the concept a little bit better. But the real concept here is that you're approaching some value of x and you're trying to determine the value of y when you get there. That's all a limit is in terms of what we're going to be doing. So I'm going to be talking about the ways to do that in a variety of different methods. We're going to start with tables and graphing. Okay, so limits utilizing graphs and tables. So our first equation that we're going to deal with in our number one here is our first example is going to be the function x squared minus 1 over x minus 1. And we want to know what's happening at this graph as it nears x equals 1. So from a limit standpoint, we would write that in the following way. The limit here as x approaches 1 of the function x squared minus 1 over x minus 1. Okay, we'll talk about algebraic methods later. For now, let's talk about the table, which is something that kind of similar to what we did in the last class. Same idea, but a little bit more involved. Okay, so let's see what happens as f of x approaches 1 using the table. Okay, so what does that mean? So we need to plug in our values of x into our function for each one of the values across the top here. So, for instance, let's look at the value negative 1. If we look at negative 1 and we sub negative 1 into our function right here, we're going to put negative 1 here. Get negative 1 squared is 1, minus 1 is 0. If we put it in the denominator, negative 1 minus 1 is negative 2. So we get 0 over negative 2, which is going to give us just 0. What about the number 0? So let's put 0 in here. We get 0 minus 1, which is negative 1, over 0 minus 1, which is also negative 1. So negative 1 divided by itself is the number 1. Okay, we can obviously do that for 0.9 and 0.99, but it's extremely ugly, so I'm just going to give you the results that you get, which are 1.9 and 1.99. Okay, you'll see that these numbers right here are clearly approaching the number 1, which in the middle here I have the limit designated. But if you go on the other side of this, you can clearly see that I'm taking numbers, but I'm approaching from the other side as well. So in the previous section, you only approach from one side. Now let's approach from both sides and sort of like squeeze it into the middle on what the value is going to be. So for example, if we put in 3, if we put 3 into the equation over here, we're going to get 9 minus 1, which is 8, over 3 minus 1, which is 2, which will get us 4. If we put 2 in, we're going to get 2 squared minus 1, which is 3, over 2 minus 1, which is 1, which is 3. Again, I could put these numbers in manually, but I'm just going to give you the quick calculations. You get 2.1 and 2.01. Okay, so as we're squeezing the value 1 in here and we're approaching it from both sides, it appears that is approaching what value once we get in the middle here? Well, I think, again, everybody's light bulb should be going off here. It appears that we are approaching 2 in the middle here, which means for our calculations, the values of f of x clearly approach the number 2. So what is this? This is the limit as x approaches 1. So what would we write? So basically, in the problem, we would say that the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. So that would be our answer to our problem. So that is using a table. We're not going to do that a lot. You're going to do it a little bit in your labs and homework, but we're going to be using more algebra / calculus methods later. But for now, we're just going to talk about the beginning methods to figuring this out, one of which is a table. Okay, well, what about a graph? So what I did was I graphed x squared minus 1 over x minus 1, the function f of x. So this is f of x equals x squared minus 1 over x minus 1. Okay, if you look at this, hopefully some of you are looking at this and going, wait, this is a line? So believe it or not, this is a line. Your instincts, in the beginning at least, should have looked at this and said, well, this is a rational function. Rational functions from pre-calculus create graphs that look something like, let's say, this, right? So there had a little, you learned how to do that in pre-calc. They create these little weird-looking things, and there's a lot of other ones that are related to that, but generally that's the case. But something happens within the algebra, which we'll talk about later, which basically forces this to be a line. Note, there's also this thing happening in the line. There is a gigantic hole in our line. So prior to calculus, a lot of your instruction would not have concentrated on this. I very rarely see it. So one of the things that you're going to have to get used to is when you're graphing something, if there's a value that absolutely does not work in the function, it's not in the domain actually, in reality, like that's the technical way to say it, then you must remove it from the graph as well. So believe it or not, this graph here is exactly what should be written. Now, if I had taken this and put it in graphing software, this hole would not be here, which means that on labs, let's say, or homework, if I give you a problem, something that where I say graph this sucker here, you have to add the hole after the fact if you're using technology. So keep that in sort of in your mind when you're doing some of those things. So this is the graph. So now let's get to, let me get rid of this here. Let's get to finding a limit if I'm given the graph. Well, look what happens. So from the left side, I'm approaching this limit. Remember, again, we need to approach it from both sides. So if I'm approaching from the left side, approaching 1, essentially, I'm walking along this line right here. And what happens as I get to, I'll do it on the bottom, it's a little bit better looking. As I get to the number 1, well, think of 1 as like a barrier here. So as I get to 1, in order to find the limit, you need to know, are you ready? You need to know the value of y as I approach 1. Or in other words, what is the height as I approach 1? Hopefully you clearly see once I get to 1, the height is actually 2. If I come from the other side, if I'm walking across this line as I'm going, as I approach this line, what height am I approaching? Again, I'm approaching 2. What does this mean? This means that, again, since both of these agree and they're approaching the same number, I would say, once again, that the limit as x approaches 2 of x squared minus 1 over x minus 1 is equal to 2. I will get into more detail later about what happens when it's not. So in this case, when we're looking at these problems, we basically have they're approaching the same height. Sometimes they don't. For now, we're just dealing with this scenario and what's going on here. And just as a side note also, just as a global look at limits, why do we learn about limits? Because there's nothing happening at 1. So we have to basically guess. If I plug 1 into this equation, this thing blows up and I get an undefined result. Why? Because division by 0. So I don't know how to find 1 directly, which means I have to find it indirectly. So the process of finding limits is finding what's happening as close to the point as possible, because you can't find anything at the point itself. Okay, so let's talk about some more limits. So it's very common in all of your studies in this class that you will get a funky graph that looks like this, that will have holes and points removed and curvatures everywhere, in which you're going to find not only function evaluations like this, but also limits like this. So the goal is for you to become an expert in doing this. So I'm going to use this example as a way to get there, and we'll be doing others as well. First things first, I want to do a function evaluation, something that you would have done in algebra. I want to find f of 1. So what is f of 1? Well, f of 1 is basically saying, what is the exact value of y at x equals 1? So again, here this is, what is y, or in other words, f of x at x equals 1. So what do? We go to 1, x equals 1, and we go up and find the value of y. Well, what is it? It is 2. Well, that was easy. Our answer is 2. Believe it or not, it gets a little bit more challenging soon. Then we go to the limit problem. It says, what is the limit as x approaches 1 of my function? Well, the whole thing is the function, so I need to approach 1. So this is similar to this right here. What do I need to do? I need to approach x equals 1. So in a sense, I'm creating a barrier at x equals 1, and I need to approach it from both sides. So as I approach the sucker from both sides, which height or value of y is it approaching? Hopefully, clearly, you get 2. So what most students get at this point is they're going, Jesus, man, this is really like super easy. Like, what? I don't really get it. So they'll often ask, aren't these always going to be the same every single time? Well, that's a great question. And the answer is most definitely no. And that's where people get very thrown off by the whole process. So let's continue on by taking a look at that. Look at 3a. So I want to find f of 2. So I want to know, what is the value of y at x equals 2? So here's 2. So what do? I go up and I go, geez, I have a hole in the line. So my question is what is f of 2? So I often get students that will go, it's undefined. I disagree. Why do I disagree? Because there is a point right here. So there is a value of y at x equals 2. It doesn't matter if it's on the line or not. That has no bearing on the situation at all. The value of y at x equals 2 is actually a bit further up the graph at y equals what? 5. Okay, that's the first thing. But what about the limit in the same scenario? So what is the limit as x approaches 2 of the function? So if I made a barrier here, in a sense, if I'm approaching 2 from both sides, what height is it approaching? Well, hopefully you see that the height that it's approaching at is 3. So the height there is 3, and it's approaching that height from both sides. So look at this. These two are now not the same. So even though it looked like in every example that was the case, that is not the case here. And to be honest with you, most of the time it's not in this class. So let's do the last couple and see where that goes. So f of 3. So we'll go to f of 3. If I go up here and I reach the point on the line, there is no point. There is nothing there. And if I go even further, there's nothing up here either, which means there is no value of y at any value of x, which means this is undefined. Okay, so let's see if the limit is undefined. All right, so what do? We need to approach 3, which is this barrier here, from both sides. So let's go this side, and let's go this side. If we approach from both sides, what height are we approaching? Well, it looks like we're approaching x equals 4, or y equals 4. All right, so this gives you a nice idea of how limits and function notation agree or don't agree on what we're doing. And believe it or not, this is going to lead to a much larger topic called continuity, which we do in the last section. But for now, this is how you evaluate these numbers when you're looking at a graph. Okay, so you can clearly see that anytime we try to find a limit, here, here, or here, we were always looking at the limit coming from each side to see if they agree. So now let's get formal about that. So each one of these three things I circled are called two-sided limits. Why are they called it a two-sided limit? Because you're basically, it includes both sides in the determination. But in order to do that, we had to find what's called one-sided limits. In other words, we need to define the left and the right-sided limit. So we're going to break down a two-sided limit into left and right side. So how do we do that? So how do we designate a right-sided limit to start? Believe it or not, it's all the same, except what we do is we have a plus sign as what it looks like. It's a superscript or an exponent. It's not an exponent, it's a superscript. But the plus sign means from the right side. Whereas for a left side limit, it makes logical sense that the superscript is going to be a minus sign. So basically, if I was to just do a quick summary of this, so if we went back to our first problem here, so if you recall when we looked at this, so where x was 1, we approached it from this side. So how would we designate that? We would say the limit of x approaches 1 from the left side, minus sign, of our function is equal to, according to this, a height of 2. Then, what about, let's do green. So the green symbol. So for green, we're coming from the right side. So we would say the limit as x approaches 1 from the right side, the plus sign, of our function is equal to 2. Because again, that's the height. Now, since these here, orange, since these agree, they are the same value, we were able to conclude that the two-sided limit is equal to 2. Okay? So that's sort of the summary of it. Now, FYI, if they don't agree in the standpoint of what you're doing, then we say not that they're undefined, that it does not... spelled that wrong. Does not exist. So we abbreviate that DNE. So just so you know, you'll be using DNE a lot. Okay, so what is that all? Let's go to a problem again, just to verify what's going on here. So it says, let's take a look at this function. Again, this is what looks like a rational function, okay, in our problem. It says, let's make a conjecture about the right side limit as we approach 2, the left sided limit as we approach 2, which means then the two-sided limit as we approach 2. So right, left, two-sided. Okay, so let's look at the first graph. The first graph clearly shows the value of f of x is approaching, well, it shouldn't say first, the graph. Get rid of the first second here. The graph clearly shows the value of f of x, which is this, is approaching what from the right side? Okay, so if we're actually approaching, remember we're approaching 2. So What is the value of 2? It's right here. So this is our barrier here. So we're approaching 2 from the right side, which is right here. What height are we approaching once we get near the barrier at 2? It's a height of 3. So we're clearly approaching 3 from the right side. Therefore, the limit as x approaches 2 from the right is 3. Okay, so again, the graph. If we want to approach the graph from our value of 2 from the left side, what height are we approaching? Again, we're approaching 3 from the left. Therefore, again, the height is 3. Our limit of x approaches 2 from the left is 3. So we can therefore say, since we approach 3 from both sides, the two-sided limit is going to be 3. So this limit would basically be 3. That's going to be the key. Okay, the one thing that's happened in every problem so far that we've dealt with is that the limits agreed. In other words, the limits coming from each side always agreed with one another, right? They agreed with one another. Here, here, here. They're always the same height. So, as I stated before, that is not going to happen sometimes, and we're always going to use the terminology DNE to represent that. So this graph, which is similar to one we did before, is going to present that in a much more clear way. So let's get started. So let's say in this crazy graph f of x, we want to determine the limit of x approaches -4 from the left side. Okay, so what are we at? So basically, this is our -4 barrier value, our value of x. So we need to approach this from the left side. So what line is active on the left side? It's this one up here. So we need to approach it. So if we're approaching along this line, approaching -4, what height does it seem to be approaching? Well, once we get to the point, the height is 3. So therefore, this is equal to 3. Now, what if we are approaching it from the right side? Well, where is there something drawn on the right side? Well, there's nothing up here anymore, right? So that's out of the picture. It looks like from the right side to approach -4, we're down on this slope down here. So if we're approaching -4 from the right side, what height are we approaching this time? Well, when we get to this open circle right here, it looks like we have a height of -2. So therefore, because the two limits that we have, the right and the left side, are not the same, not equal, we therefore say that the two-sided limit does not exist. So hopefully this is understandable to you, because how can you find a limit in a scenario where you got two different things happening? So if you have on the left side you're approaching one number, on the right side you're approaching another, then they don't agree, which means how are you going to say that there's actually a limit for the two-sided? You can't. So we would say does not exist. Do not write undefined. Undefined is only for functions, evaluating functions. So in this case, it's DNE would be our value. Okay, let's do another one. So 6D here. So limit as x approaches 2 from the left side. Okay, so now we're moving over to the value 2 over here. So if we're approaching from the left side, then we have to find the curve that's on the left side. It appears that it's this one. So as the curve approaches 2, when it reaches the end at 2, what's the height? Well, hopefully by now you guys are absolutely rocketing through this. Maybe even by yourself, you're going to get a height of -1. Now what about the right side, which is this one? Well, on the right side, the curve is now up here. So what is it approaching? It's approaching a height of 5, and because these don't agree, we say that this does not exist. Okay, it seems to be a pretty standard pattern that we got going on here. And finally, let's look at this last one here. Let's look at the number 4, which is over here. So if we're approaching 4 from the left of this barrier, we're on this line right here. It looks like we're approaching a height of 2 when we reach the end and hit the barrier. What about on this side? If we're approaching from the right, we're approaching from this part of it. And as we reach the middle point there that has no point, undefined point, What height does it appear that we're approaching? Well, these are equal, right? I'm going to write not equal here just to be consistent. These are equal, which means what can we say about the two-sided limit? It is indeed just 2. Which means sometimes it works, sometimes it doesn't. It just depends on the graph, on what you do. Often on exams, whether I'm going to be able to do that in a remote environment or not, I do put one of these graphs because it's very good to for students in understanding and truly understanding what's going on with limits. Okay, so I'm just going to follow a very common, not common, but very famous function called the floor or greatest integer function, and it's represented by the square brackets here of x. What does it mean? It's basically the greatest integer less than or equal to x. Okay, so if I were to say, just as a preview, if I was to say what is the greatest integer function of 0.5, then that would be what is the greatest integer that's less than or equal to that number? It's 0, right? Whereas if I said, hey, what's the greatest integer function of 3? It would be 3 because that's the greatest integer less than or equal to 3. So what kind of graph does that create? That creates the graph over here. It's like a little barbell-looking step function that is actually pretty clever for trying to figure out limits. So this will be kind of the more advanced problem that we've done so far. So I'm going to use it in order to talk about what we've learned. So look at 7a. The limit of x approaches -2 of f of x. So the first thing you should notice is that there are no plus or minus signs in the superscript of -2 under the limit, which means that this is a two-sided limit. If it's a two-sided limit, you've already been trained that you must find the left and right side limits before you can find the two-sided limit. And what do you need to make sure that happens with each one of those limits, the one-sided limits, that they're equal? So the first thing we need to do is we need to find the limit as x approaches -2 from the left of our function. And then we're going to find the limit as x approaches -2 from the right of our function. Okay, let's find those. So if we go to our graph, basically -2 is located right here. Okay? So we need to find the graph where we're approaching -2 from the left side. So if we're approaching this barrier from the left, it looks like we're approaching from this side. As we approach the point or lack of point that is at that barrier, what is the height? The height is clearly -3. But if we're approaching -2 from the right side, we're up on this little barbell-looking step. And what height is that approaching? That is approaching -2. Well, what does that mean? That means that the two-sided limit does not exist. All right, so removing that, let's move on to another value, 7b. What about 1.5? Okay, so 1.5, positive 1.5, is located right here. Okay, so let's talk about the same concept. Notice no pluses or minus signs as superscripts on the x value. So we have to do 1.5 from the left of our function. And a little extra line there. And the limit as x approaches 1.5 from the right of our function. All right, so let's try it. So it looks like if we're approaching this barrier from the left, we're right here. We're right on that little part of the little barbell thing. And as we reach that actual barrier at 1.5, that value of x, it looks like we have a height of 1, right? So what about the right side? So it looks like we're again on the right side of that barbell. So as we're walking across that, what height are we approaching? Look at that. So it appears that because these are the same, the two-sided limit is going to be 1. So two different scenarios, one that resulted in do not exist, one that resulted in a solution of 1 for our limit, but a very good example of how limits work in terms of what we're going to be doing. So Worth noting that in the last couple sections, basically, we started with, learning about the derivation of limits, right? And in this section, we talked about ways to use graphing and tables and such in order to figure out what limits are going to be. Very valuable, super valuable. But there's got to be an easier way because we can't always look at a graph, and that's what the next section is going to talk about, is essentially what are those easier ways.